Now dear students, let's discuss types of thermal expansions. As we have studied, when a substance is heated due to continuous increase in intermolecular collisions, the substance will expand. Now if we talk about thermal expansion types, these are classified in three broad categories, which are linear expansion, superficial expansion, and cubical expansion. Linear expansion is basically expansion in length. When a body is heated and if its temperature increases, its dimensions change, and all these variation in dimensions are studied under linear expansion. Superficial expansion is expansion in area. When obviously the dimensions of a body increases, its surface area also change, it will increase. That is considered and technically termed as superficial expansion. Cubical expansion is expansion in volume. On increasing volume, whether a body is a solid or liquid, the cubical expansion always exists. Whereas in case of liquids, we never talk about length or area of a liquid. So generally for liquids, we don't talk about linear and superficial expansions. But for liquid as well as solid, cubical expansion, which is expansion in volume, will always hold. So now we are going to discuss these three different categories of expansions one by one. If we talk just about linear expansion, to analyze mathematically the phenomena of linear expansion, let us consider a rod which is of length L. Here if we increase the temperature of this rod, say initial temperature was T1 and it is increased to T2, and say the rise in temperature delta T is T2 minus T1. So here we can say due to increase in temperature, the length of rod will increase, and say if one end of rod is fixed, the whole expansion will take place on the other side. Say due to rise in temperature, the length of rod increases by delta L, which we can call as expansion due to rise in temperature. Here this variation or increase in length depends on several factors. Like the very first factor is delta L is directly proportional to the initial length. Because if initial length is more number of particles are there in the rod. So due to increase in interatomic separation between all the molecules, overall expansion will also be more. The second point is delta L is directly proportional to rise in temperature. For more rise in temperature, more variation takes place, and by combining these two, we can say delta L is directly proportional to L delta T. So here if we transform it in an equality, here we can add a proportionality constant alpha L delta T. Here alpha we term as proportionality constant, which is termed as coefficient of linear expansion. Here alpha we term as coefficient of linear expansion. Now when we talk about linear expansion, after linear expansion, the final length of rod we can write as L plus delta L, and if we just substitute the value of delta L, this final length will become L. We can take this L common, so it will be 1 plus alpha delta T. So this is the final length of the rod after expansion. You must be careful about the results that expansion and length of a substance depends on the rise in temperature as well as the initial dimension of the substance, and mainly dimensions and length are considered for solid object, not for liquids. Similarly, we can talk about superficial expansion, which is expansion in area. Just to understand it, say if we consider a rectangular board which is having its length L and its breadth B. And we increase the temperature of this board from T to T plus delta T. That is, delta T is the rise in temperature. And obviously, if two of its edges are clamped, then on the other side, its length will expand up to this level, as L will increase by delta L and breadth will increase by delta B. So in this situation, we can simply state the initial area of the plate was LB, and after rise in temperature, we can write final area of this plate would be L can be changed to L into 1 plus alpha delta T multiplied by B can be written as B into 1 plus alpha delta T. Here alpha is the coefficient of linear expansion for the plate. So in this situation, this L multiplied by B can be replaced by A. So final area can be written as A multiplied by 1 plus alpha delta T whole square. Now in this situation, we know by binomial expansion 1 plus x to power n can be approximately written as 1 plus nx. The power can be taken in and we can neglect higher powers. This can be taken for x very less than 1. So generally it is observed that the coefficient of linear expansion is a very small quantity. So for small variation of temperature, this alpha delta T is also very less than 1. So we can write for alpha delta T very less than 1, we can use final area is equals to A into 1 plus 2 alpha delta T. Here this 2 alpha is again a constant which can be replaced by another constant beta, which can be now written as 1 plus beta delta T. And here we can write beta is equals to 2 alpha, which is termed as coefficient of superficial expansion. This is considered as coefficient of superficial expansion, and this is the relation we use for a different type of objects and having some specified surface area which changes on increasing temperature. Now, similar to the analysis we have done for superficial expansion, we can easily analyze cubical expansion. Say we have a box of dimensions L, B and H. So L is its length, B is the breadth and H is height. So we can write that the initial volume of this block can be written as LBH. And if alpha is its coefficient of expansion, we can state on increasing temperature, rise in temperature by delta T, the final volume can directly be written as this LBH 1 plus alpha delta T whole power 3. Because length will change to L1 plus alpha delta T, breadth will change from B to B1 plus alpha delta T, and H will change from H to H into 1 plus alpha delta T. And again here, as alpha delta T is very less than 1, we can use this final volume as equals to initial volume into 1 plus 3 alpha delta T. We can take the power in and neglecting the higher powers as per binomial approximation. In this situation, this 3 alpha can be replaced by gamma, which is termed as coefficient of cubical expansion. And here you can also state that for liquids only gamma exists, but for solids alpha, beta and gamma all are in existence, because for liquids we can never talk about the dimensions, length or area. So we use the direct relation final volume is initial multiplied by 1 plus gamma delta T, where gamma is the coefficient of cubical expansion. This is the relation we use. Now we'll talk about variation in density of a substance. As we know, on increasing temperature, if volume of a substance increases, its density will decrease. Say we are given with a solid object which is having its mass m, and as we know, the mass is always conserved and say its mass is a constant, and say we increase its temperature by delta T. So its volume, if initially it was V, so certainly due to rise in temperature because of thermal expansion, it will increase from V to V final. So we can say in the situation, initial density of substance rho initial we can write as m by V, and after increasing temperature we can write final density rho F to be m by volume will increase to Vf, and we know this Vf we can write as V multiplied by 1 plus gamma delta T, where gamma is the coefficient of cubical expansion for the material of this object, and we substitute it here. We can see the final density can be written as m upon V1 plus gamma delta T. And here m by V can be written as initial density, so final density can be written as initial density upon 1 plus gamma delta T. This result you need to be very careful for uses, because here several times it happens for solid object gamma delta T is very less than 1. So here we can write for gamma delta T very less than 1. Because generally solids expand less and liquid expands more for same rise in temperature. So your final density we can write as initial density multiplied by 1 plus gamma delta T to power minus 1. And this minus 1 can be taken in, and final density you can write as rho I 1 minus gamma delta T. This is the relation we use. Generally for solids we can use it, but this is not valid for substances generally which are liquids, which have gamma high, such that gamma delta T is not very less than 1. So you have to be very careful for such type of cases. If gamma delta T is not very small, you cannot use this. In that case, you need to go for this result, and if gamma delta T is very small, you can use the result. So be careful about these results and their application in different type of problems.